these are some of the topics that I'll be covering today. I also included 3 bonus topics: Mach Number, sound barrier, and Doppler effect. And as you can see, I'm going to be covering a bunch of topics today, so listen up and don't slack off. Well, to introduce myself, my name is Georgian and I love to give presentations. You can find me here. You could email me if you want, if you have any questions or want to reach out to me. Also, if you're bored, let's remember that this is physics and it is completely normal, but I'll do my best to keep you guys interested. Also, by the way, I'm recording on a cheap phone and in the washroom, so please bear with me for like 20 minutes. Firstly, I'm going to be talking about the explanation of wave terminology. What are waves? And the basics of waves and the terms. Well, what are waves in physics? A wave is a disturbance or a variation that transfers energy progressively from one point to another in a medium. The particles of a wave would temporarily be displaced, but they will always return to original position. Waves require the action of oscillating or vibrating source in the medium to be formed. Some examples of waves that happen all around us include radio waves, water waves, sine waves, cosine waves, stadium waves, earthquake waves, sound waves, and light waves. Now, what is a pulse? A pulse is a single disturbance that moves through a transmission medium. The medium can be a vacuum or matter and can be any size. A pulse is associated with a single sudden motion or impact. For example, if a pulse is moving the rope and at the end of the rope is being held firmly by someone, then you could say that the pulse is reaching a fixed end. Another example is if a rope is swung multiple times, a wave will be formed. Once will form a pulse. Now let's move on. Well, firstly, there are 2 general types of waves: transverse waves and longitudinal waves. Transverse waves are waves that the direction of which is perpendicular to the direction of the vibration of the particles of the medium. Some examples of transverse waves can be the vibration of a guitar string or light. Now, what are longitudinal waves? Well, basically, they are waves where particles of the medium vibrate parallel to the direction of the wave motion. Some examples of a longitudinal wave can be sound, ultrasound waves, and seismic P waves. Another fact is that both transverse and longitudinal waves require the movement of an oscillating or vibrating source, which is called a simple harmonic motion. The simple harmonic motion creates a wave which moves away from the source using its own velocity. Now, what is frequency? Frequency is the number of cycles that occur in a given time period. Some examples of frequency is that the human heart beats at an average of 69 beats per minute, while a baby's heart beats at a frequency of 120 beats per minute, or BPM for short. Okay, now let's talk about period. Well, what is a period? A period is the amount of time it takes a wave to complete one full cycle, or the time it takes for one complete cycle of a vibration to pass a given point. As the frequency of a wave increases, the period of the wave decreases. Frequency and period are inversely proportional and can be expressed mathematically as period equals the total time divided by the number of cycles. Okay, right now, I'm going to be talking about a very big concept and a very important one too. So listen up. Well, to get the velocity of a wave, we need to use the universal wave equation. Since we already know the formula, V equals d over t, you can use the characteristics of a wave to determine the velocity. The distance traveled in one cycle is the wavelength and the time it takes it to the period. So using those, we can make the formula for the velocity of a wave. V equals wavelength divided by period. We're not done yet. Since the period is measured in seconds and the frequency is measured in 1 per second, we replace the period with 1 over frequency. From there, we can get the universal wave equation. V equals wavelength times frequency. Now let's do an example problem. A sound wave is traveling at a frequency of 254 Hertz and has a wavelength of 1.5 meters. Determine the velocity. So we know the universal wave equation, which is V equals wavelength times frequency. So from there, we just plug in the numbers. So V equals 254. Also, by the way, I suck at using Google Jamboard, so sorry for taking a long time. So 254 multiply 1.5 meters, which we then get, let me calculate this. And we get 381 meters per second. So that is the final answer, and it was really that simple. The relationship between the period and the universal wave equation is that the speed of a wave is inversely proportional to the period while directly proportional to the wavelength. That is why the universal wave equation is related to the period. Okay, now let's do another example that requires us to find the period and the frequency. So let's head over to the Google Jamboard to do it together. Also, the reason why I'm doing another one is because this topic is pretty important and I want you guys to master it. And I'm feeling pretty nice today as well, so yeah. So this problem is Jeremy's hand vibrates back and forth 20 times in 5 seconds. What is the period? What is the frequency? So I already know the universal wave equation, which is V equals wavelength times frequency. So we do 5 divided by 20, which we then get 0.25 seconds, which that is the period. Now for the frequency, we need to do F equals 1 divided by, oh yeah, by the way, we just redid the wave equation, so we get frequency. So we do frequency equals 1 over the period, which is 0.25. Which we then get, let me calculate this again. 1 divided by, which we get 4. So the frequency is 4 hertz of the hand. And there, that's how you do it. Now I'm going to be talking about amplitude. Amplitude is the maximum disturbance of a wave from its 0 point, either positive or negative, which is measured in meters. The amplitude of a wave is used to measure the strength or intensity of the wave. A high energy wave will have a high amplitude, while a low energy wave will have a low amplitude. The amplitude of a wave is its height above the mean level. For example, if you're on a rough sea in a small boat, the distance you travel up and down from the crest of a wave to the trough is twice the amplitude of the wave. Well, that's it for wave terminology. Please feel free to go back anytime in the video if you want to go back to some place to clear something up or if you missed anything. Let's move on. Now I'm going to be talking about how do sound waves move through air. In air, the only type of vibration possible is longitudinal. Air cannot sustain a transverse motion because the air particles drift off. In the dense areas of air transmitting a sound wave, they are called compressions, and less dense areas are called refractions. The reason why your voice sounds all weird and high-pitched and helium because
helium is so much denser than air. So when it is inhaled, it shortens its sound waves so the lower tones in the voice are amplified and the higher ones fade out.
But there are many different factors that may affect the movement of sound waves through the air. Well, firstly, the speed of sound through the air is only 331 meters per second if the density is 1.29 kilograms per meters cubed. Well, basically, there are two factors that affect the speed of sound, which is temperature and density. The stiffer the material, the faster the sound will travel. So basically, the speed of sound is greater and faster in solids than in liquids. For temperature factors, sound moves faster in warm temperatures because air particles move faster as the temperature increases, but sound travels farther in cold temperatures because the sound waves bend away from the warm air and back towards the ground. Sound wave travels faster in water because sound waves travel faster in denser substances because neighboring particles will more easily bump into one another. There are about 800 times more particles in a bottle of water than there are in the same bottle filled with air. Thus, sound waves travel much faster in water than they do in air. To calculate the speed of sound in the air, you can use this formula that's on the screen right now. So take a look at it. The speed is measured in meters per second, and the temperature, which is T, is measured in Celsius degrees. So let's do an example problem using this formula. So the question is, given an extreme hot temperature of 54 degrees Celsius, find the speed of sound. So for this, it's pretty simple as well. We have the formula to find the speed of sound, which is right there. Then we just plug in 54. Then we just have to calculate 0.6 times 54, which gives us 32.4. Then we add that to 332, then which we then get 364.4 meters per second. That is the speed of sound in 54 degrees Celsius. Now I'm going to be explaining about wave interference. Well, wave interference is what happens after two or more waves meet at a particular point in space at the same time. Waves interfering can cause either constructive or destructive interference. When the component waves construct or increase the resultant wave's amplitude, there is constructive interference. Destructive interference is if the net wave's amplitude decreases and the component waves destroy each other. The waves combine to form a net wave at the point with an amplitude that is equal to the vector sum of all the involved waves' amplitudes. This is known as the law of superposition, or the principle of superposition. If you look at the diagram on the slide right now, the first wave has amplitude of x, the second wave has an amplitude of negative x. This means the vector sum results in the resultant wave having an amplitude of 0. Now I'm going to be explaining about resonance, standing waves, and harmonics. Well, resonance is when a system is driven with frequency the same as its natural frequency. A system oscillates best at its natural frequency, and its amplitude increases the most at resonance. An object is resonating when it is forced at its natural frequency. There are many types of resonance, but I'll explain one type in this video. Mechanical resonance is when an object vibrates after another source with a periodic force that is vibrating at the same natural frequency as the object. An example of mechanical resonance is two people at a playground swing. One person is swinging while the other is pushing. To get the further swings and greatest amplitude, the pushers need to be at the same natural frequency as the swing. Resonances are called by wave interference, and that's how standing waves are formed. Standing waves, also called stationary waves, is a combination of two waves moving in opposite directions. each having the same amplitude and frequency. But how are standing waves set up? Well, they're set up by standing waves patterns are characterized by points in which the medium does not vibrate, which are called nodes. Points of a wave with the maximum amplitude are called antinodes. They oscillate from a positive displacement to a negative one back and forth. There are three types of harmonics in string instruments, such as in violins and guitars. There is the first harmonic, the second harmonic, and third harmonic. The first harmonic, which is the lowest possible frequency at which a string could vibrate to form a standing wave pattern, is also known as the fundamental frequency. The first harmonic is not a wave, but a pattern of a wave. In the pattern of the first harmonic or of a guitar string, there's only one half of a wave within the length of the string. In the first harmonic, there are two nodes in the ends and a single antinode in between the two nodes at the end. The second harmonic string vibrates in two sections, so that the string is one full wavelength long. Because the wavelength of the second harmonic is one half that of the fundamental, its frequency is twice that of the fundamental. When the node is attached to the wave, an antinode is added as well to maintain the alternating patterns of nodes and antinodes. In order to create a regular repeating pattern as seen in the first node, the node must be located in the middle of the two original nodes. The second harmonic has three nodes and two antinodes. Now I'm going to explain the third harmonic. The third harmonic has the highest frequency. The third harmonic of the string is produced by adding two nodes between the ends of the string. As with the previous two harmonics, if two nodes are added to the wave, then two antinodes as well in order to maintain the alternating pattern of the nodes and antinodes. The additional node and antinode gives the third harmonic a total of 4 nodes and 3 antinodes. So let's do a standing wave problem. So the question is, a standing wave occurs in a bathtub. Baby Hank is jumping up and down and the nodes for the small waves are 15 centimeters apart. What is the wavelength of the wave Baby Hank is producing? Well, since we have the distance of the nodes, which is 15 centimeters, and we don't have the wavelength, so we need to do 2 multiplied by 15, which you get 30 centimeters. So the final answer is the wavelength of the waves that Baby Hank is producing is 30 centimeters. Now I'm going to explain the question. What does the speed of a wave along a string depend on? Well, to start, we know the speed of the sound depends on the medium it travels through. So we can deduce that the speed of the wave depends on the properties of the medium it travels through. Properties of string include tension, length, density, and diameter. We can combine length, density, and diameter to get the mass per unit length called the linear density, which will be the mass of the string divided by the length. The thicker the string, the higher the mass, which we can get the equation V equals square root divided by linear density. V is the velocity in meters per second, T is the tension in newtons, a meter's length is the linear density in kilograms per meters. Okay, right now I'm going to teach you about the Mach number, which is one of the bonus topics that I included in today's video. So the Mach number, named after physicist Ernest Mach. Mach 1 is designated as the speed of sound at a specific air temperature. Speeds below Mach 1 are called subsonic. Speeds over are called supersonic. And speeds greater than or equal to Mach 5 are called hypersonic. To find the Mach number, it's very simple. First, calculate the speed of sound at the given air temperature, which would be Mach 1. Then, divide the speed of the plane by the Mach 1 value previously calculated to get the Mach number for the plane. So now, I'm going to talk about the sound barrier. So when a plane is close to the speed of sound waves will build up in front of the plane and squeeze together, which forms a pressure wall, which is called a sound barrier. This occurs because the plane itself is catching up to its sound noises and it requires a ton of excessive energy to break the barrier. Eventually, the plane will break the sound barrier, but obviously only very fast jets can break the sound barrier, like fighter jets, those ones. But After it breaks the sound barrier, it will leave a pressure wake behind it. The wake has two pressure waves, also called sonic shock waves, spreading in an expanding cone shape from the plane nose and from the wing tips. If the shock wave was strong enough to reach the ground, we would hear two loud sonic booms like boom. Otherwise, the pressure waves would have dissipated along the way, not reaching the ground. But to sum up the sound barrier, look at the diagram on the right. Okay, so the final topic that I'll be teaching about today is the Doppler effect. The Doppler effect occurs when planes or cars are traveling way less than Mach 1. One example is a train. The train gets louder as it is approaching and the sound diminishes after passing by. Same goes with planes. Look at the diagram on the slide. If an ambulance is stationary, like at rest, the waves move out uniformly and are heard by both person 2 standing from the ambulance and person 1 standing behind the ambulance. Because the waves move symmetrically, the wavelength observed by both people is the same. In the second diagram, the ambulance is moving away from person 1 and approaching the other. Sound waves are compacted in a moving direction, and the wavelength of the sound waves to person 2 are now smaller. Person 2 gets higher frequency sound waves and thus a higher pitched sound. Person 1 is in the opposite situation, where the frequency decreases, the wavelengths increase, and the sound is lower pitched. Now refer to the last diagram. This one is slightly more complicated. The car moves towards a person and covers VOT distance. A sound wave from the stationary car has wavelength 1, so the sound wave of the moving car will have a wavelength of 2. To solve for wavelength 2, we replace the t with the period of the wave t to get wavelength 2 equals wavelength 1 minus VOT. To find the frequency of wavelength 2, we reshape the universal wave equation, so it is V equals wavelength F to F2 equals V divided by wavelength 2. Then, substituting for wavelength 2 for wavelength 1, subtract VOT, we end up with F2 equals V divided by wavelength 1 minus VOT. But since wavelength 1 equals V divided by F1 and T equals 1 divided over F1, so we can use S for sound, so the final equation becomes F2 equals F1V divided by V minus VO. The change in frequencies, named the Doppler shift, is F2 minus F1. But what if the ambulance drives past the person and is moving away? Then the first equation is changed to wavelength 2 equals wavelength 1 plus VOT because the new sound wave needs to travel the distance of a stationary car's sound wave, the distance traveled by the moving ambulance. The frequency equation is also changed to F2 equals F1 V divided by F plus VO. The combined equation is F2 equals F1 V divided by V plus VO, where it specifies an approaching source and shows a receding source. Okay, now let's do a Doppler effect example problem. So the question is, Hank is running toward Jeremy at a speed of 15 kilometers per hour while yelling his name. Calculate the apparent frequency of the yelling heard by Jeremy. The sound has a frequency of 200 Hz. Assume a speed of sound of 334 meters per second. Well, already they gave us the speed, which is 334 meters per second. That's the speed of sound. And we know the speed of Hank, which is 15 kilometers, but remember to convert to meters per second, which you divide by 3.6, which you get 4.2 meters per second. And we know the frequency, which is 200 Hertz. But we need a second frequency of the yelling. So we have the formula, which is at the bottom left. F2 equals F1 multiply V, the speed of sound, then divided by speed of sound minus the speed of Hank. So you plug in the numbers 200 multiplied 334 divided by 334, subtract 4.2, which we get, let me calculate this. Which we get 202 hertz. That is the apparent frequency of the yelling heard by Jeremy. So that's all for today's video. I hope you enjoyed it and I had fun teaching you guys as well. And if you're still awake, well, thanks for listening through my video. Also, feel free to go back anytime in a video and pause if you want to watch something or listen something again. And yeah, thank you again and have a good day. Also, by the way, my email is at the bottom, so if you want to contact me, feel free.